So we're still cleaning up that the data set because we don't want to send a whole bunch of junky detections to Matt. But we should be submitting new discoveries from ZTF done with this algorithm in the next couple of weeks or so. So this was really fun. And what it allows you to do is it allows a couple of things. One is it allows you to operate on telescopes without having to have them come back in the same night. But then it also allows you to do archival searches. So now you can, it used to be that if you want to find asteroids, find new asteroids, you have to have a survey that observes with this pattern. So 2 observations within 30 minutes or so. So it means that there's a ton of archival data out there that's not really suitable for discovery of objects using those kinds of algorithms. Now we can go back to that archive. So one of David Niederberg's students is actually doing that with the point source, with the NOAO point source archive, trying to go back and see everything that we can dig out of that. For LSST, if we can make this this algorithm work well on NEOs, because we do not want to lose that population, it means we can potentially unconstrain the cadence. So we don't have this revisit time, and it makes all surveys future and past asteroid search compatible. So in essence, any survey that does observations on the sky, we can feed it with something like this and see if there are rocks in there. All right. So now, given the time, I'm going to ask, can we do even better? And then I'm going to say, ask me after the question time. But let me skip to my conclusion. Whoops. The thing that I'm trying to get across here is that the solar system has kind of been a sleeper science topic in the LSST area. We've talked about it a lot in the context of finding near-Earth objects, finding potential killer asteroids, but where I think really the gain is going to be is in potentially in the science of the creation and evolution of the solar system that gets enabled by these huge increases in samples. And all these increases in samples will arrive in the first few years of LSST. It's very timely to start thinking about that now. And the reason why we can do that is A, we're building bigger telescopes, but B, because we're having better algorithms that can extract information from them. And the more we think about it, LSST is already kind of at the large end of the spectrum. We're getting into the LHC type era of experiments in astronomy, which is not necessarily great because you can only have a few of them and far between. But where there's a huge, I think, open territory or potential for opportunity is improving how we analyze and how we make use of those data sets, making sure that we actually extract all the information. So here, with just a few of us thinking about it, we went from ON cubed algorithms to analog N type algorithms for extracting asteroids, and the ability to extract these kinds of information, this kind of information from a broad set of surveys, not just from LSST. I think going forward, given the next mission is going to be like a couple of $1 billion likely, this is where a lot of the gain is. If for 10 million you can construct an algorithm and a big enough computer to execute it and make your survey a factor of even a few percent better, it's worth it. So this is just something to think about. All right, I'll stop there and thank you.
Thank you, Mario. Avi.
So you mentioned the improvement in obviously the telescope sensitivity and the algorithm you're using, but there is one additional improvement which is quite important in the solar system, which is that you're looking overall the sky. So, I mean, most previous searches were focusing on a rather narrow plane, right? So, wouldn't you expect that to bring in many new, potentially objects that you haven't anticipated?
Yes. We know from theory that there should be some in polar orbits that are interesting. So, for example, Sarah Greenstreet, I mentioned at the beginning, she did this the model of the current NEO population, and has shown that there's dynamics that take some of their orbits and flips them. And in the process of the flipping, they spend a lot of time in what's called polar corridor, where they're orbiting essentially with 90-degree inclination. That population is very unexplored right now, just because nobody's looking there. And the ability to of LSST to go and look there, the ability to actually use other telescopes that have observed there for good reasons, because we all want to avoid the ecliptic and the galaxy if we want to do extragalactic. Like that's what I think is going to be tremendously useful in the next few years. So one example there is NASA has tentatively greenlit this mission called the NEO Surveyor. It's I think a $700 million mission to go to L2 and then look for NEOs in the mid-infrared, near-infrared. This mission is
L1.
L1. Sorry. This mission is currently constrained to about 60% of the sky around the ecliptic, because the argument is we need to have many revisits to detect NEOs. We don't have time to unconstrain it. So one of the things we're trying to do here is kind of race against time and demonstrate that these types of algorithms work, so that you can then take what's effectively an infrared telescope in space and turn it into not just a planetary defense mission, but in a proper astrophysics mission, all sky maps in 2 IR bands. So that's I think that one of the benefits of looking into this.
More questions? Yeah, go ahead.
So you said that the hope was that maybe you could make it so LST wouldn't have to revisit fields even once. Presumably in terms of hitting the depth you want, that's baked into the calculation. So what would the actual efficiency gain be if you were able to achieve that?
So the way I think about it is it's removing a constraint on cadence, and then you can make that decision based on what your other science cases demand. So an example here might be, if you were doing dark energy, you want to cover as much of the sky as possible in as many different conditions as possible, so as not to introduce any systematics. So if you're doing dark energy, you would want to cover the entire sky every night, and make sure that no part stays uncovered in a given weather pattern, so you don't accidentally imprint something. If you're doing supernovae, you may want to come back anyway. But now you don't have to come back at 30 minutes. You may decide you want to come back in an hour, if that's more useful for that science case, or in 2 hours. So it just unconstrains a whole region of parameter space for cadence optimizations. That's the way I think about it.
Oh, go ahead.
Does it, in a sense, though, bring in a new constraint in that you still need enough points on the arc in order to link them? So if you select a case such that you end up missing recoveries altogether, then you might end up.
Yeah. So for this test, we explicitly want to take that into account. We said, so with LSST, we're going to have 3 tracklets in 2-week period, because LSST roughly covers the sky every 3 nights. So after about 9 nights, technically you've covered everything 3 times, and you should have enough data in there. So here we said, let's see if we assume that we cover the entire sky. Let's see if we find everything in a 2-week period that has 5 observations anywhere in the 2-week period. So in that sense, it's certainly no worse than what LSST does now, because right now we have to have 3 pairs in a 2-week period. Here we said 5 observations, so it's 1 less than with the 3 pairs effectively. So this is a little muddled, but I think I hope you got the gist of what I'm trying to say.
Yeah, I think what confuses me is that you say you're saving visit time or something, but you still have to visit the asteroid.
Oh, I see.
Time,
Yes,
right?
you still have to come back, but you don't have to. The argument here is that you don't have to come back in 20 minutes. You can decide to come back every 2 days, if that works better for your science case.
Does it affect the quality of the orbit solution you get if you're predicting when the next accuracy?
I would naively expect the answer is yes, but it's probably not noticeable. And here I would look at math. So the question is, if I have 3 vectors and 3 points versus 6 points evenly distributed across the track, which orbit solution would be better? The latter. And I would assume the latter, but Steve Chesley is thinking that, we all agree that it should be the latter, but in terms of quantitatively how much better, like Steve is arguing that marginally better, but I've never actually tried it.
I would agree with Steve, but test it out.
Yeah, we'd try it out.
I think once you have an arc of like more than a week, more than one observation and at night, really just, it's effectively one observation. Because the motion within like an hour is insignificant compared to the motion across many nights.
Okay, I would like to close with sort of a question of, do you think with LSST are we going to sort of map, or like how far into the outer solar system are we going to map? Or will we see sort of the end of the, I mean, I guess it's hard to predict, but anyway, along those lines.
we can detect, it depends on how massive and bright or shiny, I guess, the objects are out there. We can detect motion out to about 150 to 200 AU based on the current cadence and current software. With slightly different software, which LSST is not signed up to delivering, but one of the many clever people in the audience can write. We should be able to push that much further. And one of the things that I didn't get to, but I'll use this opportunity to do, is one of the things we're looking at is can we stack the individual images using shift and stack techniques in the outer solar system to push. So if we bunch up about 10 observations in 10 days in LSST, then we have enough computing capacity and we have the algorithms to stack those, find deep KBOs out to a volume of about factor of, and I have it written down here, factor of 5, right? Factor of 5 large discovery volume for KBOs and for planet X. And interestingly, the way the size distribution for KBOs works there that way, the number of KBOs you discover grows linearly with your exposure time. So effectively here, if we increase our exposure time by a factor of 10 by stacking 10 images, we may get 10 times as many KBOs.